Hello everyone, my name is Shadeeb Hossain and I'm actually affiliated with Will Cornell Medicine. This presentation is on my topic that I'm presenting at the IEEE. Let me start sharing the screen so that you guys could understand what I'm talking about. So here is the presentation. So the topic that I'm going to present today is hardware requirements for 2D cylindrical high-pass ladder coil design that would enable a homogeneous excitation in ultra-high field MRI. So these are my qualifications as you could see on the screen. So I do have an EIT, Electrical and Computer Engineering. I did complete my master's from Central Michigan University, and I completed my PhD from the University of Texas, San Antonio, and I do have an MBA as well. I would also acknowledge the support from my co-authors, which is Dr. Victor Taracila, Dr. Fraser Robb, James Moore, and Dr. Simon Angela Winkler, who's the PI for this project. So, exactly what is this topic about? So, let me start with a brief introduction. There are almost 30 million scans done in the United States alone every year. Among the other parts of the MRI scan, there's one major component, and that is the transmitter and receiver RF coils. So, what does this receiver and transmitter RF coil basically do? What happens is when a patient goes in an MRI scan, there's a uniform static magnetic field, which is measured in B naught. And this is the Tesla. Like you have 7 Tesla, you have 3 Teslas. So what happens to hydrogen atoms, which is inside the individual's body, they tend to align, creating a magnetic moment with the static magnetic field. You could see in this diagram, this is how a schematic of an MRI scanner looks like. You could see over here, there's the main magnet, and then there's the RF coil. We over here are designing the RF coil for 7 Tesla. That's the main objective. So our main objective over here is to design a head coil for 7 Tesla RF. So what would happen that RF transmitter would generate electric pulses, and the frequency of these electric pulses is equal to the Larmor frequency. Now, depending on the strength of the static magnetic field, there's a fixed Larmor frequency. Since my project is focusing on the 7 Tesla MRI scanner, so the design has to be tuned for 298 megahertz Larmor frequency. Now, when you're dealing with such ultra high frequencies, there's several challenges to it. One of the challenge is that it creates a non-uniform magnetic field distribution, A, and the second is it has a higher specific absorption rate. So as you increase the strength of the magnetic field, there are certain challenges to it. And this can be overcome with the right tuning of the RF coil. Now, in industry, we have always used the bird cage model. So you could see towards my left over here, this is a schematic. This is exactly a prototype of a bird cage model. A unit segment would usually consist of the inductive and the capacitive component. And design that we are working on is inspired by Dr. Ballone's 2D cylindrical high pass ladder. So this is a little different, significantly different from this design, and there's several advantages to it. Now, why are we interested in the RF coil? What does the RF coil actually do? It is important that the RF coil plays a critical role in the image quality. Okay, so you as a radiologist, or if you are in that department, you would want a very good image quality so that you can detect the minute details. So the designing of the RF coil plays a significant role in the signal to noise ratio, the signal uniformity, and the signal image resolution. This is a simulation model. You could see over here, these are the two simulation models of the field distribution for the bird cage and for the 2D cylindrical high pass ladder. You would see, compared to the birdcage model, the 2D cylindrical high pass ladder has a more uniform field distribution. Now, that is very important. You want a more uniform field distribution because this would in turn affect the image quality and the SAR values. So I'll go into detail how a 2D cylindrical high-pass ladder is constructed, but as you could see from here, each resonating element consists of an L and C component, the inductance and the capacitance component. So it will consist of fixed value capacitors at the four ends for each single element, followed by a variable capacitor to tune it to a desired frequency, and they are easily coupled with adjacent resonating elements through transverse coupling, through longitudinal coupling, and through diagonal coupling as well. I'll go into more details in the next couple of slides, but this introduction is just to show you a contrast in terms of the prototype of how a 2D cylindrical high-pass ladder differs significantly from the birdcage model that is used in the industry. And it is important because, as I've shown you, that it helps you to produce a more uniform field distribution, and also improves the signal to noise ratio. So, as I've mentioned earlier, that this design is actually inspired from Ballon et al. 1994. When he came up with the prototype, he does have a pattern on it as well. So what happens is you have to choose an array of elements, a particular length of the array of elements. So in this case, supposedly we give it numbers like m is to n. So each of these resonating elements has to be, first of all, tuned to a resonating frequency. Let it call F naught. Okay, so I want each of these elements over here, as you could see over here, tuned at F naught. Now, since they are all at the same frequency, this one, and all of these resonating elements are at the same frequencies, when they are brought in close proximity with each other, what would happen? Because of the coupling, inductive coupling between them, there would be a shift in resonance. The coupling would be along the transverse direction, along the longitudinal direction, and also along the diagonal direction as well. Uh, Now, the thing is, as an engineer, it's because very important to mathematically calculate these values of the coupling, as well as what are the generated eigenfrequencies over here. The coupling coefficients are actually calculated from this equation that you will see over here, and the generated eigenfrequencies for different modes is calculated theoretically using this equation. Now, as I've discussed earlier, that a single array actually consists of fixed value capacitors over here. In our case, we use 12 picofarad capacitors at the 4N, followed by a single variable capacitor. The inductance is due to the copper foil, so the length we took is 6 times 8, and the thickness is 1.1 centimeter. So this is a single array, a single resonating element, and this is a planar resonating element. They're arranged like this. In our prototype, we just stuck with the 6 times 4, but definitely it depends on the size that you're trying to use. Because if it's a whole body coil, it would be a different size. If it's just the head, it's a different size. If it's just the hand, it would be a different size. So it depends on that. So this is the planar model, and this is the cylindrical model. Now, when we tried to do the bench testing, we had to calculate the coupling coefficients, right? So what happens is, this is a pickup loop. A pickup loop is basically connected to a network analyzer, and that helps you to see the resonating frequencies. So each of them has been tuned at different frequencies. Initially, we'll start with particular frequency, and then we'll try to see the coupling, the shifting that is occurring, the deviation that's occurring from its resonating frequency because of the longitudinal and transverse coupling. And we found that in most cases, it's between 7 to 8%. Now, the thing is, one of the major challenges over here is that you have to tune it. Each of the resonating element has to be tuned at a particular frequency so that it eventually helps you to achieve the targeted 298 megahertz. So we started with 269 megahertz. We did with different frequencies, but for the sake of our uh, like presentation and for the sake of a paper, we just focused on like three examples. So we started with like 269 megahertz. We tuned each of this resonating element at 269 megahertz. So we found that there are a couple of eigen frequencies, but it did not help us reach our desired 298 or 300 megahertz. That's is what we need to tune our RF coil for 7 Tesla. Similarly, with 275 megahertz, our eigen frequencies were not falling within that frequency range. But however, when we use a 286 megahertz frequency, you would be able to see that it did reach our desired 298 megahertz, 300 megahertz range. And this was measured using the same pickup loop, which is connected to a network analyzer. So we tried to connect it with the theory. So our imaging mode, in this case, these are the different eigen modes over here. So these are the different modes. So the results that we found with the practical are in close proximity with the theoretical ones with the different eigen modes. But this is our imaging eigen mode because we require the theoretical to 98 megahertz. So conclusion future works. Basically, this paper discusses the hardware architecture of a 2D cylindrical high-pass ladder, particularly for a head coil that is tuned to 298 megahertz, which can be used for 7 Tesla. We came to the conclusion that when each of the resonating element for this particular model, when it has 12 picofarad capacitors at the four ends, and the inductance is 6 centimeter. Each of this resonating element is 6 centimeter times 8, and thickness of 1.1. Only when you're individually tuning each of this resonating element at 286 megahertz, only then we're getting the desired 298 megahertz, which is the imaging mode. The coupling coefficients in this case we found along transverse and longitudinal direction along the 7 and 8%. And the results that we found in experiment are in good agreement with the theoretical values, as you could see over here in the previous slide, as I showed you. These are the theoretical ones, different eigenmodes, and you will find these results are very close with the practical ones as well. So for future work, I would say that what we would try to work is creating a whole body coil. Obviously, this would mean that it would require a much larger dimension. Instead of the 6 times 4, it would increase the size. It would definitely change the eigen frequency in individual resonating frequency as well, which will in turn affect the eigen frequencies as well. Uh, Obviously, what in this case, we have like 6 times 4, right? 24, of which 12 of them are actually active components and the 12 are passive components. So since it's a 6 times 4, we would have 6 active feeding ports because it's like 6 along this direction and 4 along this. So 6 of them active. We would need 6 of them active feeding ports, which we would place along the cylindrical framework, and they need to be connected to a preamplifier, and there has to be a phase difference of 60 degrees between each of them to create a more homogeneous field distribution, as I've shown you earlier. And it's always best practice to have like the impedance, avoid an impedance mismatch, so you have to make sure that's also taken care of. This is some of the future works. So uh yeah, definitely I would like to acknowledge uh, like Cynthia Fox in proofreading the manuscript. Also, this is a funded project from the NIH and the GE Healthcare. And yes, if you have any questions, please feel free to shoot me an email or ask me if we meet in person. But yeah, so to summarize, we actually tried to develop a 2D cylindrical high pass ladder, which is an RF coil for 7 Tesla. We realized when each of this resonating element is tuned at 286 megahertz, only then you are being able to reach the eigenfrequency of 298 Larmor frequency, which is required for our 7 Tesla. The capacitors we used was 12 picofarad capacitors at the four ends, with followed by variable capacitor in order so that you can tune it at different frequencies. The length of the uh, inductor was 6 times 8 and the thickness was 1.1. Obviously, if you're trying to use it for a body coil, you'll have to change the inductance and capacitors, and you need to change the size of the array, so you'll have to work accordingly. Well, anyways, thank you for the opportunity, and I would like to thank Will Cornell Medicine for supporting this project, and IEEE Symposium uh, of Industrial Electronics and Application for helping me with this, for letting me present this, uh, giving me this platform to present this topic. Thank you so much.